All right, so in this section, we're going to look at solving congruencies. Okay, so this is like solving equations in mods, using mods. Okay, so first kind of equations we're going to solve is linear congruencies like this. You notice there's a variable in here. I have AX is congruent to B mod M. So our goal is to figure out what X values make this congruency true. We're going to be given the value of A and B and M. Those are given integers, but we're trying to solve for X. And in the second part of the section, we're going to solve systems of linear congruencies. Okay. So in order to solve for X, like if we had any kind of equation, let's say we had a linear equation like this, 2x equals 12, then to solve this, we want to multiply both sides by the inverse, the multiplicative inverse, right? We want to multiply both sides by 1/2 in order to get x equals 6, okay? So before we solve the congruencies, we're going to talk about inverses, okay? So modular inverses. And so this fundamental theorem of arithmetic right here says that if a and m are relatively prime integers with n is bigger than 1, then an inverse of a modulo m exists, and that inverse is unique. All right? So basically, of the inverse of a in modulo means this. It means that I can find a number a bar that if I multiply it with a, this is going to give me 1 in modulo m. Okay, so notice this is very similar to regular arithmetic, right? That if I can find a multiplicative inverse of a number so that if I multiply it itself, I get 1. But in this case, we're looking at getting a result of 1 in modulo, okay, when you sort of take the remainder. So let's look at, we're going to do a couple of examples of finding inverses, and then we're going to jump in and solve a linear congruency. Okay, so I want to find the inverse of 3 mod 7. Let's do it by inspection first. Okay, so then we're going to worry about the Bezout coefficients. So if they're small numbers, you can easily find these by inspection. So basically, we want to look for a multiple of 3 that is 1 more than a multiple of 7. Okay, so we're kind of looking at a modulo 7, modulo m. We want to look for a multiple of a that is 1 more than a multiple of 7, a multiple of m. Okay, and this is because we want to end with this. We want to end with sort of that number. So the a bar a, inverse of a times a, to be 1 mod 7. So the difference between that multiple minus the number that we're dividing by, the m, has to be 1. So that's why we want it to be 1 more than the multiple of m. So let's start listing multiples of 3. So multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, so on. See if we need more. Multiples of 7 are 7, 14, 21, and we can stop because we can spot what we need. Okay, we can spot that 15 is 1 more than 14. So I found a multiple of a that's 1 more than a multiple of m. Okay, so I can write 15 is congruent to 14. Oh, sorry. get rid of this to 1 mod 7. Okay, because 7 is going to divide into 15 minus 1. Okay, and I wanted a multiple of 3 because I can break 15 up into 5 times 3 is 1 mod 7. Okay, so this was my original A right here, and this has to be the inverse. This has to be A bar. Okay, so an inverse of A is 5 because this property is true. That's the definition of an inverse of a number in modulo. Okay, the product of the inverse with the number gives a result of 1 in that modulo. Okay, so inverse of 3 in modulo 7 is equal to 5. Okay, now in modulo, that inverse is not unique because I could have a bunch of numbers that multiply 3 and give me it's congruent to 1 mod 7. So it's not unique. Actually, if I take that 5 and I add or subtract any multiple of 7, okay, is an integer, then that will also be an inverse. Okay, because let's say I take 5 plus 7, which is 12, right? Then 12 times 3 is going to equal 36, and 36 is congruent to 1 mod 7, right? Because 7 divides into 36 minus 1, right? So whatever your mod number is right here, that inverse value that you found, if you add or subtract any multiple of that mod of the 7, that will also give you an inverse. Most of the time, we want our inverse to be the lowest positive integer. That's probably the one that's easiest to work with. But sometimes you don't need to go with the lowest positive integer. All right. So with small values, you can do things by inspection because you can compare multiples. But if the values get bigger, then it's not so easy. So this is where the Bezout coefficients from the last sections came in, because the Bezout coefficients allow me to find the inverse in modulo. Okay, so let's go through that process and see how that happens for the same example. So let's find the Bezout coefficients of 3 and 7. Okay, so we start with the Euclidean algorithm first. So 7 is 3 times 2 plus 1, right? And we have 3 equals 1 times 3 plus 0. Right, so this is the GCD. GCD of 3 and 7 equals 1. And if I solve the equation for the GCD, I get 1 equals 1 times 7 minus 2 times 3. Okay, so the inverse of 3 mod 7 is going to be the Bezout coefficient of 3. So the inverse of 3 modulo 7 is the Bezout coefficient of 3, that A value. So in this case, the Bezout coefficient of 3 is -2. Okay, so if we compare with what we've done by hand, we saw that we found the inverse to be 5, not 2. But remember that the inverse is it's not unique. It can be that value plus or minus any multiple of 7. So this leads us into saying the inverse is -2 plus or minus any multiple of 7. All right. And if I want to look at the lowest positive value, then I take -2 plus 7, which gives me 5. Okay, so that's the same answer as before. All right. So let's look at another example where we find the inverse with larger. Okay, so let's look at this example. So find the inverse of modulo 101, or find the inverse of 101 modulo 4,620. So this is like my A and this is my M. Okay, so we need to find the Bezout coefficients because comparing multiples, not so practical anymore. All right, so we're going to find the GCD first with the Euclidean algorithm. Right, so we're going to start with the larger number and divide until I get a remainder of 0. So we're gonna follow through a few steps. So 4620 divided by 101 is going to be 101 times 45 plus a remainder of 75. Okay, so we take these. So 101 is 75 times 1 plus a remainder of 26. We'll take these. 75 is 2, 26 times 2 plus a remainder of 23. Okay, I'm going to take these. 26 is 23 times 1 plus a remainder of 3. Take these. 23 equals 3 times 7 plus a remainder of 2. 3 equals 2 times 1 plus a remainder of 1. And 2 equals 1 times 2 plus a remainder of 0. Okay, so first non-zero, remainder is 1, so that's the GCD of the two numbers. Okay, now the Bezout coefficients. We're going to work in reverse. Right, so we're going to start here and solve for 1. So I'm going to get 1 equals 2 minus 1 times 2. Then we're going to solve for 2 here and plug it in for this value. I have 1 equals 2 minus 1 times 23 minus 3 times 7. I think this is a 3 right here. Yeah, from here, 1 equals 3 minus 2 times 1. Okay, so distribute this negative, and I'm going to get 3 minus 1 times 23 plus 3 times 7. Okay, so now this 1 times 3 and 3 times 7 are common. They're like terms, so we're going to combine them. We get negative 1 times 23 plus 8 times 3. Right. Now we're going to go to this equation, solve for 3, and plug it into here. So this is going to be negative 1 times 23 plus 8, 26 minus 23 times 1, which is going to equal negative 1 times 23 plus 8 times 26 minus 8 times 23. Collect like terms, so I get 8 times 26 minus 9 times 23. Okay, so go to here and plug in for 23. So I get 8 times 26 minus 9 times 75 minus 26 times 2, which is 8 times 26 minus 9 times 75 plus 18 times 26. Collect these together. I get 1 equals negative 9 times 75 plus 26 times 26. All right, plug in for 26 from here. So 1 equals negative 9 times 75 plus 26. 101 minus 75 times 1, which is, let's see if I can do this in one step, 26 times 101 minus, so I have the 9 and the 26 times 1, 9 plus 26 is 35 times 75. All right, final step here, plug in from 75 from here. I get 1 is 26 times 101 minus 35 times 4620 minus 101 times 45. So this is going to equal negative 35 times 4620 plus the 26 here and the 35 times the 45. 35 times 45 plus 26 gives me 1601 times 101. All right, good. So that's the end of it. These are my Bezout coefficients. Okay, so the one I'm looking for, right, is the coefficient of 101. Okay, so then because I'm looking for the inverse of A, I need the coefficient, Bezout coefficient of the 101 number. Okay, and this is the 1601. So my inverse is 1601. And it could be any plus or minus any multiple of 4620. Okay, so the inverse is the coefficient, the Bezout coefficient of the A, the 101. But again, you can add and subtract any multiple of the mod, and that would also be the inverse. But this looks like this is the first positive value, so we're going to go with that. Okay, so it's quite a process to find the inverse. All right,